All right, welcome back to the channel and another Mind Your Decisions YouTube channel puzzle breakdown. So I saw this one recently, and the link to this video will be down in the description. It's 6 impossible puzzles. Can't tell you what the last 5 are. I haven't looked at them. I just saw the first one and I thought this is kind of cool. And I'm not going to go through and explain how Presh worked this out logically. You can go and watch this video for that one. But what I wanted to do is to see that if you expanded this problem into something that you couldn't juggle in your mind, because this is a rather small set, and you can kind of keep this stuff straight in your mind and logic out how to get from room 1 to 8 going through alternating color doors. That's the puzzle. And this is a small enough set you can do this in your mind. But immediately when I look at this, I think, well, what happens when you expand this to something that you can't juggle in your mind? How would you be forced to switch from juggling this logically with the limitations of our mind into being forced to be using some sort of mathematical model? So yes, that's how my brain works when I look at stuff like this. So this is why I find these things so interesting, because it immediately forces me to want to expand upon what Presh does here, which is mostly just logic building, which is great. But my angle on this is always, let's expand this to the point where you can't logic it out so cleanly. And what type of mathematical model would you use? And if I'm ever bringing these things to people on my channel, you darn well know 100% of the time I'm going to be using linear algebra, LA. Matrix math is just unreasonably good at solving problems, and I've highlighted this a time or two on my channel. And this is going to be another one. And I would almost say, if it wasn't too pathetic as a human being to say, that LA might be my first love. Now, of course, that's not actually true, but it's close. And understand the powerful tool that LA is. I mean, it's literally the backbone that AI is built on. So take that for what it's worth. So the puzzle is get from room 1 to room 8 by going through alternating color doors. So Presh used blue and red doors. Over here you can see I'm using red and green. The reason why is I like to screw with you RG colorblind people. So his blue is my green. So again, I'm not going to walk you through how he did it. He logicked through it. But how would we do this if we needed a rigorous mathematical algorithm? So first of all, you separate the red. I'm going to just use green in place of blue, even though you see it here. You separate the red and green doors and you put them on a plot. So over here on the left side would be you're in room 1 and you need to, or you're going to room whatever across the top. Same thing on the green matrix. So we have a red matrix and a green matrix. So we encode this information into red and green matrices, 2 different ones. So for example, to get from room 1 to room 2, you're going through a blue/green door. So in 1, out 2. So if you can do it, it's a 1. If you can't, it's a 0. And understand something, and that's all we're doing here. So you can figure that out. We do this with the red doors. We do this with the green doors. Now understand one thing here. Let's just take a look at 2 and 6, for example. So in 2, out 6, you can tell you can do it. If you can go from 2 to 6 through a blue door or green door, you can go through from room 6 to room 2. So down here, 6 and 2 also has to be a 1. These are 2-way doors, not 1-way. Right, so what that ends up doing is you can see in this matrix as well as this matrix, it ends up creating a symmetric matrix. So if you draw a line from top left, diagonally bottom right, you'll notice the lower half is the same as the upper half. Same thing on both matrices. So that will signify that these doors go either way. And if you aren't symmetric and there's no restrictions here on a 1-way door, you've actually inputted something incorrect. So double check if you want to do this on your own that these are both symmetric matrices. Okay, so now you have encoded this room into 2 matrices. So what are you going to do with this information? Okay, so what if we multiplied these two matrices together. Okay, so now I should back up for a second, and just let you know, matrix multiplication is not the same as you multiplying just two numbers. Everyone understands that 5 times 8 is equivalent to 8 times 5. In matrix math, that's not the case. Okay, it could be, but it's the general rule, it's not going to be, and it's not likely to be. So order matters in matrix multiplication. So let's multiply these two matrices in what I'm going to explain to you is the proper order, and you'll see why, and see what the resultant matrix is, and see what that means. See if we can decode what that multiplication does. So the order is, we'll first have to go through this blue/green door. And then the next one, by the rules of the puzzle, is a red door. So when we're multiplying it, the first door we're hitting is the green one. So our order of multiplication would be green times red. G times R is how we're going to determine. So if we multiply these two matrices, G times R, let's just see what we get. See if we can understand what that means. So green times red, if we're doing additive color here, I guess that turns into yellow. This is the matrix we get. Still some zeros, still some ones, but you can see over here we've got a 2, and over here we've got a 3. So I just kind of put this into a heat map. So what does this mean? So we've done G times R. So that means first we go through the green door, and then we go through a red door. So let's decode this. So let's just pick one here. 6 and 3 has a 1 here. It didn't have it over here. So 6 and 3 has a 1. So what this is saying is, if we're in room 6, we have to go through a green door, then a red door, because that's what we did here, green door and a red door. Can we get from 6 to 3 by going through a green door and a red door? So 6, over here, over here. Yeah, we could do it. All right, so what does this mean? 6 and 6, that has a 2 in it. So if we're in 6 and we have to go through a green door then a red door, basically it's saying we can get from 6 to 6. What this is telling you is there's two ways of getting from 6 to 6 if you go through a green door and a red door. So let's logic this out. 6 to 2 and 2 to 6. That's one way. And what's the other way? 6 to 5 and then 5 to 6. Now, it doesn't matter that you can go 5 to 6 through this red door or this red door. It's still 2 steps. So what this matrix encodes is, first of all, can you get from one door to another at all? Zeros, you can't. Going through a green door and a red door. And if you can, this actually encodes how many times you can do it via the 2 steps. So that's what that multiplying those two matrices together encodes. So you can probably understand what we're going for. We want to go into room 1, start in room 1, and we want to come out in room 8. So the important cell is this guy right here. So what you end up doing is just multiplying green times red times green times red. That's you alternating the doors. That's part of the rules. And you continue to do that, multiplying this matrix by green and the resultant by red, and you step through and you stop when you see the 1, 8 over here be something greater than 0. And you can understand there may be multiple ways to do it with just one extra step. So the 4, 6 here, you did it 3 times in 2 steps. 6 is kind of popular, if you'll notice, because it's just this like a central room and you can get there a lot of different ways. So 6, you'll see, is very popular. So if you do that, you'll find you have to do that 7 times and you come up with this matrix. So the first 6 times this was 0, the 7th time, so it's green times red, that's 1, 2, 3, 4, 5, 6, 7. You end with a red. Remember, you have to end with a red because you need to go through the red to get from room 6 to 8. So you'll finish on a red. So 7 times you finally get the 1 in this corner. And if you look at the heat map, you'll actually see, look at how just popular room 6 is. This is saying you can get from room 4 to 6, 42 different ways. That's what this matrix, multiplying these matrices in that order, tells you. Okay, first of all, it's possible, and this is the number of steps that it takes to get through from 1 to 8. You can't do it in less. So if you were to multiply these matrices, what you would come to first is, yes, it's possible. It takes 7 steps through, but you wouldn't actually know what the steps were. But at least you would know it would be possible. And then you'd have to go back through here and manually do it. But this is the mathematics behind finding if it's possible and how many steps. Now, so what I'm going to do here for you, I'll just put it right here through the magic of MATLAB. You can see this is the command window. So the question you're probably asking is there a way to find out what that path is? Well, yes, of course there is. Now that is outside the scope of this particular video, but I can show you through a program that I have written, and I'll just run this right now. So start at room 8, or start at room 1, end at room 8, alternate colored doors starting with green, and let's find out what that path is. So I will run that. It gives me the solution path 1 2 3 4 4 3 2 6 8. So 1 2 3 4 4. By the way, I call room 4 the Bruce Jenner room. So you can come in as Bruce Jenner on the Wheaties box, and you can leave Bruce Jenner on the Wheaties box, or you can go through here and you can leave as Bruce Jenner in a dress. So this is the cross-dresser room right there. 1 2 3 4 4 3 2 6 8. That's the path. And we can, of course, look at it. There's a nice little graphical that this program does as well. So you just follow. The gold is the solution. Now you can't shortcut it. You just got to follow the gold arrows. You can't do 1 2 6 8. You have to use them all. So 1 2 3 4. This one over here is 4 wrapped around itself. 3 2 6 8. So this program actually doesn't know what the solution is. It just keeps trying solutions, and when it finds it, it goes back to find out what the path was that it finally got there. And if there was multiple paths, like say this one, 3 times, it's only going to give you 1. It won't give you all 3 options. So let's just take a look at this, for example, and you'll see we can just change this. So we're going to enter in room 3, and can we get to room 7? All right, so I'm just changing the parameters here, and let's just run this thing. Yes, it says 3 4 4 7. So let's take a look. Whoops. 3 4 4 7. That's correct. So you can see that there is a rigorous mathematical, and this just, you can see it here again. You got to start at 3 4 4 7. So you can see there is a rigorous mathematical process, and it begins and ends with this type of matrix setup. We multiply them within the rules of this game, and there's a rigorous mathematical model that will find the solution. Is it possible or not? And then once it's found it, remembers and goes back and traces the path that it took, because the model that does this finding of the path actually just goes ahead and tries all of them blindly. It doesn't know beforehand, because how could it? It goes through and blindly follows all the different possible paths, and once it finds it, it just remembers the path that it took. All right, enjoy. We'll talk to you soon.